Friends, welcome to Chemistry Simplified. In this video, we are going to learn how to classify a normal and an inverse spinel. So let's get started. The basic formula for a spinel is AB2O4. So for a normal spinel, your A2 plus ion should take up the tetrahedral voids, whereas your B3 plus ions take up the octahedral voids. This is the general arrangement in case of a spinel. In case of a inverse spinel, your B3 plus ions take up the tetrahedral void, A2 plus and remaining B3 plus ion takes up the octahedral void. Okay, this is how the arrangement in case of a normal spinel and an inverse spinel. So how to find out which ion takes place which hole? We can find out by calculating the crystal field stabilization energy of each ion. So let's see with an example FeCr2O4. So the ions involved in this case are Fe2 plus and Cr3 plus. So DL shell electronic configuration for Fe2 plus is 3d6 and for this is 3d3. So we know that the D energy level undergoes splitting when they form a complex. So for an octahedral splitting, it gives rise to T2G and Ag energy level. Likewise, we are drawing the same for Cr3 plus, T2G and Ag. So we are going to fill up the electrons. So 1, 2, 3, 4, 5. We always go for high spin complex. The reason is the oxide ion is a weak ligand. So always high spin complex. So we are filling up for the Cr3 plus as well. So now we have to calculate the CFSE. So CFSE is given by 0.4 for per electron in T2G. There are 4 electrons here, minus 0.6 per electron in Eg, that is. So this is 1.6 minus 1.2, that is 0.4 delta naught. So in this case we have calculated. Likewise, we can calculate for Cr3 plus. That's going to be 0.4 into 3 minus 0.6 into 0. So that's going to be 1.2 delta naught. So from the value, it is evident that your Cr3 plus ion has a higher crystal field stabilization energy. So it occupies the OH hole. So it gets a normal spinel structure. So I repeat, we took the ions, we find out their electronic configuration, then we just arrange them for octahedral splitting. We always go for high spin complexes. Then we calculate the crystal field stabilization energy for the octahedral splitting. Then we compare the value. The one with the higher value will go to the octahedral site. In this case, it is Cr3 plus. It goes to the octahedral site, whereas your obvious this goes to the TD. So we'll see the next one. So the next one here we are going to deal is nickel gallium. The ions involved are Ni2 plus and Ga3 plus. Electronic configuration is 3D8 and 3D10. The D shell configurations we have given. Now we are going to find out the CFSE for them. So we are going to fill the electrons for gallium. So fill that. For nickel the filter. So we are calculating the CFSE in this case again. So you could see that CFSE is given by 6 times of 0.4 minus 2 times of 0.6. So that's going to be 2.4 minus 1.2, that is 1.2 delta naught. In case of gallium, it's going to be 0, so you could calculate it. So 6 times of 0.4 minus 4 times of 0.6, they're going to be 0 delta naught. So it is evident that in this case your 2 plus ion has a higher CFSE value. So your this goes to OH and this goes to the tetrahedral void. Hence this will be inverse spinel structure. So let's get back to this question, CSIR question. So you could see that option 1 cannot be true because your Fe goes to the TD hole, whereas option 2 says like Fe goes to TD and Na goes to octahedral site, and this should be the right answer. I hope you understood how to calculate or to find out whether which will be going to octahedral site and tetrahedral site based upon the CFSE, and classify between spinel and inverse spinel structures. Thank you.